Hi there, my name is Jungyi, a graduate student from Carnegie Mellon University. Today we present Dynamics Regulated Kinematic Policy for Egocentric Pose Estimation. From a video captured by a head-mounted camera only, we aim to infer and simulate 3D human pose and human-object interactions, such as sitting on a chair or pushing a box. Here, we ground our pose estimation inside the physics simulation and achieve physically plausible human motion and human-object interaction estimation. To achieve this, we propose to synergize the two main aspects of human pose estimation, kinematics and dynamics. Kinematics, or dynamics-based approaches, study human motion without considering the forces that cause it. These methods directly output the joint angles. Dynamics, or dynamics-based approaches, study human motion that result from forces. These methods will involve a physics simulation, Mujuko in our case. Basically, you would control a humanoid to estimate poses. And to tightly integrate these two, our framework consists of two main aspects: a universal humanoid controller and a dynamics regulated kinematic policy that works in tandem with this controller to estimate pose inside simulation. And we first propose a universal humanoid controller. This controller is capable of driving simulated humanoid to mimic a broad range of human motion. The input is one frame of target pose to mimic, and the output at per step is joint torques. This controller is compatible with the SMPL human model and can successfully mimic up to tens of thousands of mocap sequences. We use the standard reinforcement learning and motion imitation to train our controller, and compared to prior work, we learn from a much larger human motion database. The whole amassed 10,000 motion sequences. We also incorporated one of the most recent advances in humanoid control, the residual force control technique, for improved stability. The result is that a given reference human motion, our controller can follow it without additional training. Here we show the result on motion imitation using testing sequences from the human 3.6 million dataset. And we can see that our controller can mimic it without additional training and with high fidelity. Thus, we believe this controller is task agnostic and can be used in a lot of different post estimation tasks. Now that we have this controller, a naive way of using it is to use it as post processing. First, we can estimate it kinematic pose, and then we can use this controller to mimic the estimated motion. Now, the problem with this approach is that the kinematic pose estimator can still produce artifacts such as floating or foot skating. And by attaching a physics based controller and wishing that it will fix everything is not realistic. Our humanoid controller will try to correct these problems, but it becomes increasingly difficult if the regressor come up with some challenging or extreme poses. Thus, we propose to tightly integrate these two and devise a kinematic policy that directly operates inside the physics simulation. Instead of attaching the universal humanoid controller at the end without any feedback to the kinematic model, we form a closed loop system where the kinematic model will receive feedback from the physics simulation. Now, concretely, our kinematic model consists of two main parts. First, we have our initialization model. Given an input video sequence, this model computes the first frame humanoid pose, object state, image features, and camera poses. Notice that the object state contains the 6 degrees of freedom object pose and object class, which we use as a strong prior for our kinematic model. And here we use an off-the-shelf object pose estimator and detector, ARKit. The initialization pose and object state are then used to initialize the physics simulation, while the rest of them are used as per frame features for the model. Then we have our per step kinematic policy. It takes in the per stamp feature and computes the per time step kinematic pose. The kinematic pose is then fed into the universal humanoid controller to drive the humanoid, which passes through the physics simulation, and these simulated states are then used to compute the next time step pose. Notice that this feedback loop is crucial, as this allows the kinematic model to factor in the current simulation state and adaptively output the reference motion. Leveraging our learner universal humanoid controller, our kinematic model becomes a physics-based policy that outputs the reference motion instead of joint torques. Basically, we abstract the humanoid control problem into the universal humanoid controller and turn this problem into outputting reference motion. Basically, pose estimation. And to optimize this model, we leverage our novel formulation. Basically, by using this universal humanoid controller, our kinematic policy only output kinematic pose, and we can directly optimize this output based on the reference motion from the mocap studio. Before passing through the physics simulation, all the calculation is differentiable, so we can optimize our policy through supervised learning, similar to the Dagger algorithm or behavior cloning. After the physics simulation, it becomes non-differentiable, but we can still optimize the output through reinforcement learning and reward maximization. And to evaluate our models, we obtain two datasets, one captured in mocap studio and one in the real world. Each of them have 4 different actions: sit down, avoiding obstacles, pushing a box, or stepping on a box. For the mocap dataset, we capture paired first-person video and ground truth human pose. This dataset contains 266 motion sequences, and 80% of this dataset is used for training, and the rest of 20% of them is for testing only. For the real-world dataset, we captured 183 real-world motion sequences using a head-mounted iPhone. And notice that this dataset is drastically different from the setting of the mocap's dataset, featuring different objects, rooms, and subject. This dataset is also only used for testing. We have never trained on a real-world dataset. And to compare, we use 2 state-of-the-art methods, one kinematics and another dynamics. We used the official implementation of both of these methods and then normalized the input such that every model is using the same set of input for a fair comparison. Quantitatively, our model outperformed the baseline with a wide margin on both the real-world and mocap dataset. Especially on the challenging real-world dataset, our method have a much higher human-object interaction success rate, which is the most important metric. Here, we show qualitative result on the holdout test set from the mocap dataset and the real-world dataset. On the mocap dataset, we can see that our model performed well on almost all motion actions, while the state-of-the-art methods have very large drift of the human root and low success rate of the human-object interaction. Notice that all of the object movement, especially pushing the box, is a result of simulation. And we only use the estimated object pose to initialize the physics simulation. So this box movement is from simulation instead of our pose estimator. Here we shows the challenging stepping motion, which involves a lot of dynamic movements. And noticeably, our universal humanoid controller has never been trained on human object interaction tasks such as stepping. And here we showcase results on the real-world dataset. Here, our method can still extract reasonable human pose and human-object interaction. And we can see the pace, the subject, and the scenario is drastically different from the motion captures dataset. Though our method outperformed the state of art by a wide margin, our method is still limited. The humanoid can still lose balances on challenging poses, and we're training only on a small dataset and requires known object and actions as a strong prior to constrain the problem and actually make it more solvable. Our method also does not handle head rotation well because we only have the front facing view. Future directions include modeling fingers and hand motion for fine grained manipulation and human object interaction modeling from egocentric point of view. And we also believe that developed pipeline framework can be used for third person pose estimation, as well as estimating human and scene interactions. So, to conclude, we propose, for the first time, a method to estimate physically valid human pose and human object interactions from egocentric point of view. Our method can enable a broad range of applications such as egocentric pose estimation, telepresence, and manipulation, and can be essential for future augmented reality and virtual reality applications. We also hope our developed framework can be used for future works that ground human pose modeling inside a physics simulation. Our code and data will be released for future research purposes, and we thank you so much for listening. Please refer to our paper for more details. Thanks again.